So we will be talking about duality of linear programs. It is very often the case in mathematics. So it's not limited to optimization and definitely not limited to linear optimization. But it's a very common thing to have is that a problem or a task of computation or a functions representation or what have you has some kind of alternative representation whereby solving a problem can answer, solving a simpler problem may answer a more complex problem in the original domain. So what you do is you start with a problem or start with a function or start with some kind of a object, you provide us some transformation to it, and then you receive what is called a dual. It is something that you can map into, and then you can map back into the original from the dual. And some questions become different to answer. So answering one question in the original, or sometimes called the primal problem, is equivalent to answering some other problem of the answering some other question regarding the dual. So this duality situation is probably known to you from other courses. An example of something akin, it's not called duality there, but something akin to duality is like take certain type of functions and you take their Laplace transforms. So for instance, you have a differential equation that has certain properties. You can do what is called a Laplace transformation, and then you can find that you need to solve a completely other problem, not the original problem, but some other problem in the transformed domain. You get a solution, and then you can then map that back to the original domain, and you get a solution to, let's say, a differential equation. In probability calculus and probability calculus, what you can get is you have certain things like you have certain things like distribution, and the distribution has a representation through what is called the PDF or the probability density function. Then you can apply a certain transformation to the probability density function where you get what is called the moment generating function. And then answering certain problems becomes easier. If you have the moment generating function, you can find certain aspects of the probability distribution better than using the probability density function. Also in frequency domains, for instance, you have what is called the Fourier transform. So the Fourier transform transforms us from the time domain to the frequency domain. And then your representation of the function is with respect to certain frequencies, not with respect to certain points over time. So answering some questions in the frequency domain are easier than in the time domain, and vice versa. So these two representations give the possibility of answering some questions about the object or entity in question more readily than others. So this is a more general and abstract concept of duality, which is not formally mathematized here, and I don't want to make it. I just wanted to give you examples of situations very similar to the duality here. Luckily, in this case, the dual of a linear programming problem, a linear optimization problem, is very simple to calculate. So if you have the problem, let's call it the primal or the original. I'll be using both of these terms, the primal problem or the original problem. So the original problem comes at minimizing of C transpose X subject to AX equal to B, and X should be a non-negative. This is called the LP or linear problem. And its dual is another linear problem whereby you are asked to maximize a function B transpose U. Note here that the B here in the cost part in maximization are in the objective function part, the B transpose, the B is from the original problem's constraint B vector B, and subject to A transpose U is smaller than or equal to C. So you have the transpose of the matrix, and your constraints are now something has to be smaller than or equal to, and the components will be the components of the cost vector, where this U is to be a free variable. Now, the dual and the original have very fascinating relationships. So we will always consider the primal. In this material, it is mentioned that it is not necessarily the case, but for our purposes, we will focus on primal or original problems that are in the standard format where there it's AX is equal to B. Now, there are two possible ways to derive the dual, and we're going to be using definition 3.15 in all of our exercises. I urge you to do that. It is possible to use what is called the table 3.1, which gives another alternative duality. Both result theoretically in similar results, and we can discuss the dual regardless of which way it was done. But if we are to take the approach that every LP problem is given in the standard format, where it's of the form LP in definition 3.15, then we should use definition 3.15. The table gives you transformations between different aspects of the original problem and the dual of it. So if you have a maximization problem, the dual becomes minimization and vice versa. If the constraint of the maximization problem is smaller than or equal to, then the corresponding variable will be greater than or equal to. If the corresponding constraint is greater than or equal to, then the corresponding variable must be smaller than or equal to 0. If the constraint is equality, then the variable will be free. And then I think the variable and constraint are the wrong way around here in the second one. So yeah, there's an error there. Somehow it's switched. So a greater than or equal to 0 variable becomes constraint. It should be smaller than or equal to, not larger than or equal to. So there's an error already here. It's of no consequence here because we're not going to be using this table 3.1. We're going to be using definition 3.15. But if you were, you could use it to this example 3.16. So the dual, why do we work with the dual? I mean, this is very simple. It's very simple. You take the transpose of the matrix, basically, you switch B and C, you have new decision variables, and the new decision variables are free, not non-negative. First of all, the dual, I mean, if we look at it, if we take up the LP problem, let's take something that we can obviously say. If we take the LP problem, we assumed that the number of rows in matrix A is greater than the number of columns, sorry, smaller than the number of columns. So X is a vector that is far longer than the vector B. And C transpose, well, it's a vector with the same length as X, so it's a longer vector. But in the dual, we are maximizing a function of variables that have a B transpose U. So it has as many variables as the LP has constraints. So there's fewer variables there. The subject to A transpose U smaller than or equal to C. So they are somehow constrained to being constrained by the costs of the original, but not equality. And this U is now free. It can assume negative values as well. We shall see shortly what this is. Why do we do this? There is the duality of this 3.17. I'm not going to go through these examples. There are ways by which you can go to, and you can just change the problem in of the dual to the primal and so forth. So what we really want to have is between the duality in 3.15, where the original is a minimization problem and the dual is a maximization problem. So we have the LP and the DP. The theorem states that if you solve the dual, find any solution to the dual, something that satisfies, remember here, satisfies this DP problem. If you find a solution to it and you take another solution of the LP problem, then the DP problem is a lower bound to the LP problem always. So the values that the DP problem gets as its cost function will be a lower bound to the values of the LP problem. And because we are looking to minimize the LP problem and maximize the DP problem, I mean, if we are interested in the DP, then what is far more interesting is that the value of the cost function will be equal in the optimal solutions of the LP and DP respectively. So you can think of the duals as, so you have this problem of minimizing something, and I'm trying to wave my hands here to give you this idea that we are looking for a linear constraints, is like a polygon or something. We're looking for this minimum point of the LP problem. And then we take that LP problem and we take its dual, and then the dual becomes a maximization problem. And what happens is that these two meet at the point, well, they don't actually meet, but the cost functions meet. The cost functions will be equal at a point in which the LP and DP are both solved. So this gives us an idea about analyzing the dual problem in a way that will help us solve the linear problem. So that we'll provide an algorithm shortly for utilizing this. So let's prove this. Well, the proof is fairly simple. You can start with the constraint A transpose U is smaller than or equal to C, which can be transposed so that U transpose A is smaller than or equal to C transpose. And if you multiply all with X, you get U transpose AX is smaller than or equal to C transpose X, because X is non-negative. So you are just multiplying everything with a non-negative number on the left, and you're multiplying everything with a non-negative number on the right. So obviously it holds. And because AX is equal to B, you can just write U transpose B is smaller than or equal to C transpose X. So this is fairly simple algebra to show that B transpose U is smaller than or equal to C transpose X. So that's easy part. It's the easy part. The other thing is that if you have feasible solutions, so that one is, you know that all feasible solutions of the DP are smaller than or equal to all solutions, you know, all feasible points of the LP, then, you know, you have this situation that C transpose X is equal to B transpose U, and you can prove this fairly easily from what we said before. This is actually not, it's actually a little bit missing in some parts. So, okay, what you can do is you take what was said before. You take what was said before and C transpose X will be always smaller than or equal to any C transpose X. Yeah, it must be an optimal solution. Yeah, that's, yeah, right, yeah. sorry, I had forgotten that this is actually so straightforward. So what happens here? What happens really? We get a lower bound from the DP problem, okay? We get an upper bound for the DP from the LP problem. That's good. So this gives us already a lot to work on. So let's look at what we can do with the dual. So let's define some interesting thing here. If we have a basic solution or the basis for the linear problem, then we can define what are called the simplex multipliers. They're called pi b, by defining it as a transpose of C transpose B times the inverse of B. So this is, where does this come from? Why do we do this? Why do we do this? This comes from the fact that this is basically the cost part of the basic solution. Remember that the cost vectors, those components of the cost vector, the Cn, that are in the non-basic part of any basic solution, then the corresponding x's will be zeros. So those have no effect on the cost really at that point, at that basic solution point. So because if you have a basic solution point, we're only picked to certain variables. These would be the B variables. So the part of the C, the cost vector that corresponds to the basic variables is picked. That has an effect on those. And this B inverse, if you multiply this with B, the B vector, B, remember this capital B inverse times the constraint B vector gives us actually the basic feasible solution. It gives the X that is the basic feasible solution. So we're basically, what we're doing here, we are looking at the right-hand side. This is like without the X, the cost without the X. Sorry, the cost without the B. And now we can use this so that if we have an optimal basic solution for the linear problem, then at the simplex multipliers will be equal to B transpose pi. The cost function will be equal to B transpose pi, sorry. If you calculate the simplex multipliers, then C transpose X star is equal to B transpose pi star. So it's going to be this. This is going to happen at the optimal solution. So we're going to have the optimal solution of both the DP and the LP, and we can get the DP solutions by just figuring the simplex multipliers. And this is fairly straightforward proof. We start with the linear programming problem, basic solution. We calculate the reduced cost functions, which are positive. And then we kind of slip in there. Remember, there's the C transpose B inverse N. So we can slip that into that definition of the reduced cost. We notice that the pi appears there. And we notice that this reduced cost B part, again, will have the simplex multipliers there. And then we can calculate the cost function here. It becomes A transpose pi star. So that this pi star will be a feasible solution to the dual. So basically what happens is that we can calculate the simplex multipliers and try those, whether they are feasible for the dual. If they are feasible for the dual, then what we are dealing with is an optimal solution. So this can be thought of as a alternative way of detecting whether the point is optimal. So optimal solutions exist if and only if we are at a point where the dual and the original have the same solution. And that follows from this theorem very straightforward way that if they have feasible solutions, then both have finite optimal solutions and the optimal values are the same. The thing is, and the very important part here, if the linear problem has a feasible solution, but not a finite optimum, meaning that it's unbounded, it goes to negative infinity, then the dual problem is empty. It has no solutions. This is obviously easy to prove because if you think about it, every solution to the dual problem is smaller than or equal to every solution of the primal or the original problem. Now, if the original problem has an unboundedly small problem solutions, then the dual cannot have any solutions because all their solutions should be smaller than or equal to all the solutions. So you can take as small a solution as you want, and you'd still have all the solutions smaller than or equal to that. And that obviously doesn't happen. So it's fairly easy to see that the feasible set of the dual problem is empty. And we can rephrase it one more other way. This is the so-called complementary slackness. It comes from the fact that if we have feasible solutions of the original and the dual, we can simply calculate this. What happens is that the cost function x transpose C minus x transpose A transpose U will be equal to 0 if they are actually both optimal. Well, this is just one more way of rephrasing it. But one way to do this is to look at the variables in this feasible solution. The corresponding component of x must be equal to 0, or the corresponding constraint rho in the dual must be at its limit, Ci. So one of these happens for every single variable of the problem. So what it means is really that we can think of this as there being two possibilities for a variable. If we think of its role in the dual and in the original, in the primal. Think about it this way. We have the original problem. Here's the very wide and not so high matrix where the constraints here, and then there are these columns correspond to the variables. If we are solving a problem, then the so-called complementary slackness means that there is no slack in one of two ways. Either the corresponding x variable here is at 0, or now we look at the dual, we flip this in this way, and in the dual, the corresponding row or the corresponding constraint row has a value that is equal to the constraint. It must be smaller than or equal to, but if it's equal to it, then there is no slack, if you will, in that particular row of the dual. So the limits are in the optimum solution. The limits are hit in one of two ways. In the primal, x is 0, or in the dual, there is no more slack in the corresponding constraint.
Sorry to interrupt. So this means that if in the LP problem this variable, this component is equal to 0, then in the dual problem, then you must satisfy the equality.
No, it says that if you are at an optimum, then either x is at 0, or in the dual, the corresponding row is at equality. So one of two things happens. X can be something non-zero. If it's non-zero, then the corresponding row in the corresponding constraint in the dual is at the limit. It's equality, right? If it's not at equality and x is not 0, then we are not at an optimum point, right? So the complementary slackness means that there is no one of these problems has kind of taken away all the slack. X is at 0, or x is at non-zero, but if you look at the dual, the corresponding row is at its limit, equality.
Okay, I think I got it.
Remember that this duality exists only when we are in the optimum. If we are not at an optimum, then obviously the corresponding cost is something else. I mean, the LP problem has a cost that is greater than any corresponding DP problem. So it's only when LP and DP problems coincide, they have the same cost. And then if we look at the rows of the constraints of the DP problem, and we look at the columns or the variables of the LP problem, then one of these things, I mean, either the corresponding variable at the LP problem is at 0, or the corresponding constraint row is at the limit in the dual. Right. So let's go. So I'm not going to be using this here. It can be used to devise what is called the primal dual algorithm, which takes into consideration both the primal and the dual at the same time. We're alternating between solving those and moving between them many times over. Not going to go through this in great detail. I just want you guys to understand that the dualities, the important part you take away from this part here is to understand really this weak duality. Theorem 3.19 is the thing that you need to understand, and also definition 3.15. So definition 3.15, theorem 3.19, those are the things that you should take away from this. And let's look at the so-called dual simplex algorithm. I'm just going to skip to this, how it works. The dual simplex works in the following way. We find out what is called the dual feasible basis. So basically, if we find a feasible basis for the dual, we solve a corresponding basis of the primal or the LP problem. If it's feasible, we have found the optimal. Otherwise, we choose an index where this corresponding X variable is negative. And then what we do is we go to the same procedure. The only thing is that we are looking at the negative side of things. So let me just explain. I'm not going to go through this theory because I don't think I'm not going to demand you understand this dual simplex algorithm in that detail as the simplex algorithm. But in this situation, you can have a solution to the primal problem that is not feasible really, but it's still a basic solution, but it's not feasible basic solution because some of the X variables are negative. So what you can do is have what is called a dual feasible basis. I mean, the corresponding variables or the corresponding rows in the LP problem are the ones that you're looking at, and then they correspond to variables where X is negative, and then you switch it over, but you're looking at the dual and you're trying to make them positive, and then you're using the duality to detect when you have arrived at an optimal. So these are basically the two basic solutions that you can use, or two algorithms that you can use. I'm not going to ask you to learn this, and this just approaches the situation in a different way. I just want you to understand what this duality means in these terms, you know, theorem 3.19, basically theorem 3.23 as well, and definition 3.15. We don't have too much time for it. I don't want to use too much time to go through this. I mean, the dual simplex algorithm is something that if you want to really understand it, that's fine. But I am content with you guys learning the simplex algorithm, and we'll be happy with that. Let's have a small break now and talk about sensitivity a little bit shortly. Now, so the following material I'm going to talk about is a bit off topic, not off topic, but not core material in the sense that is not compulsory reading material. It is, however, of great importance to those who will be using linear programming and subsequently similar other materials, similar other models to model some real life phenomenon, which is subject to small changes. So the LP problem is very commonly a situation where you have constraints that are material or financial or temporal, meaning time constraints, or similar other resource constraints. And then what happens is that, you know, in fact, you can think of the formulation as a function of the constraints themselves, meaning that you have the formulation, it has a certain solution, let's say the minimum exists, and it is a feasible solution, it's not unbounded, and it has a feasible solution with respect to the costs and the constraints. So assuming that the matrix A for now is fixed, assuming that the cost function C is fixed, then what happens if the constraints are relaxed in some way? Because the B is a parameter, and the optimal value of the problem depends on what the B is. And if the B changes to delta B, meaning the constraints change, then it may result in new optimal values. It doesn't have a direct effect on what the cost necessarily is, but if the optimal basis changes, the optimal value will also depend on this new change. And of course, it comes into play as the basic vector does change a little bit based on what that B is, because it's calculated using the basic part of the matrix inverse times B. So what happens is, if you have a small change, let's call that delta B. And then what happens is that the optimum basic solution does not necessarily change. So at every point, X, if we move the B a little bit, then all the costs pertaining to the corresponding X's change a little bit. So you can think of, I mean, you can get a slight graphical representation of this, because if you think of a linear constraint, it's a linear constraint is a plane basically set in space. If you think of three-dimensional situation, and for now, let's assume now that there are slack variables, yes, but the original is like, you know, smaller than or equal to some plane that exists here. So this is smaller than or equal to some B. So if we increase the B, then this this constraint is relaxed, right? If we relax this constraint or we tighten this constraint, then this plane goes down. So we're pushing the X's down. And if we're increasing it, we're pushing them up. Obviously, I mean, it depends on which direction this plane resides and what the change is, okay? Remember also that we're dealing with x's that are non-negative, and the basic variables x's are always positive. And if we have a small enough change, because the basic variables are calculated by taking the basic part of the matrix, calculating the B vector with its inverse, and we get positive values, then if they're positive values, meaning none of them is zero, then if we change B even just a little bit, then the result is also positive. But obviously the x's may be diminishing or increasing with the change in the B vector, but the cost remains positive. So if it doesn't change so much that one of the other basic solutions becomes better, then what we have is we can look at the net effect on what happens to the cost. Remember, the cost is the basic part of the cost, so that's the CB transpose times X. But X is obtained in the XB. XB is obtained by multiplying the B vector with the basic part of the matrix. So what we obtain here really is the original cost plus then the simplex multiplier, which we just calculated, the simplex multiplier times delta B. So we can think of it that as long as the change is small enough so that we're not moving into a different basic solution, then we can think of the simplex multiplier as the derivative of the solution with respect to the constraint vector. So if we change the constraint vector, then the simplex multiplier by 1 unit. Again, remember, we may not be able to move it by 1 unit, but marginally, if we're moving it by 0.0001 units, and then the B vector in some direction, then the corresponding component of the simplest multiplier gives us, the proportionate change of the cost function in the optimum point in that direction, so that these can be thought of, the simplex multipliers can be thought of as marginal costs of each of the constraints. So if you think about it, that you're constraining some optimum solution, you're trying to minimize the cost, and you have some constraint which says that this constraint needs to be satisfied. And then on the right-hand side of them, there is a value that constrains certain variables. Then, you can think of the simplex multiplier as the marginal cost of changing that particular constraint a little bit. So because the limit is there, then there is a certain derivative, if you will, partial derivative to the solution. So the solution changes when you change this. So that's why we can think of it as a marginal cost of that constraint. So for instance, if we constrained in some industrial process, we are constrained that you need this for 1 unit of our product, we need 1 ton of steel, 2 tons of gravel, 3 tons of plastic, and 5 tons of something like this. And then when you add these two together, then you need to make 7. You make 7 of these. I don't know, let's say you're building something, 7 units of something from these, 7 tons of something, you get some, I don't know. And then that constraint, you need to do this, use this many of these resources to get 7 of those things that you need. And if that 7 changes to 8, then this corresponding multiplier tells us what happens to the optimum solution of your optimization problem. Assuming that the change is not so big that the basic solution changes. If the basic solution changes, then obviously the optimum is found at another point, and this consideration no longer holds. Here it's explained And one other thing is to look at what is the sensitivity to the change in B. So how much can B change before it is results in the change of the optimum, you know, a quality. If you think about it, a qualitative change in the optimum, in the sense that you now, you know, no longer want this basic solution, you want the other basic solution. And this can be found by the following algebra. I'm not going to go into great detail here, but if you think about this, we partition the function in the columns, and we get a basic solution. Let's call that x tilde or x squiggly x, which is the original x plus then the corresponding change, net change incurred by this change in the B. And if we look at these components, each in their own right, you know, you want to find a situation where it's what is the, well, I'm not going to go through this algebra here. The algebra here is meant to find the condition that when does one of these components of B change so much that we need to change the basis. So that's sensitivity in some sense, that, you know, how sensitive is it to have to find another basic solution if we change one of the constraints. And yeah, here's an example of it. Not going to go in detail in here. So another thing that happens that you can analyze, again, remind you, this is extra work in some sense, that you don't have to learn this, but you have to be aware that this kind of considerations need to be done and can be done in general to optimization problems. And we don't have the scope in this course to do this in very in-depth manner, but I'm just going through them here. So the first two subsections consider what happens to the optimum when you're changing the constraint B. But what about if you change the cost function? So for instance, you're minimizing some costs, and your inputs are, you know, crude oil, uranium, I don't know, steel, I don't know, apples, potatoes, and water, or something like this. And then, you know, the changes in prices happen. So when we change the cost function, what happens to our optimum? When do we find the optimum solution there? And the optimal solution does not depend on this cost. Well, the optimum, this is wrong. It says optimal solution does not depend on C. The optimum solution does depend on the C, but what meaning the feasibility of a solution does not depend on C. So if we change the cost, then what happens is the cost changes, but the solution never becomes infeasible because of the cost changes. But what may happen is a previously optimal solution may become non-optimal because of the changes in the costs. So for instance, let's say we were running some kind of an industrial process that has several different possible energy inputs, and the relative changes of these different energy forms changes, then at some point you want to phase out one of the ways of getting energy if it becomes too costly, or you may start using some other form of energy or electricity or whatever if the cost of that goes down. And the way we do this is to look at the reduced costs, and here the reduced costs come at very, very handy. And this is you know, some of you said that it's really hard to understand what the reduced costs say. Well, the reduced costs are basically the cost of increasing something that is now zero. It has components corresponding, the C n hat has corresponding components to each of those variables that were not our basic solution. So those variables that were 0, we're not using those resources in our solution. And the reduced cost at the optimum mean that they're all non-negative. So they're positive or 0. And if a cost change occurs in the original cost in terms of a non-basic variable, let's say J, and that changes by some delta Cj. And now we get this condition that the reduced cost should still be 0. Sorry, non-negative. So we're looking at the condition that is that says that as long as the change is not great enough to make this corresponding reduced cost negative, then it doesn't change the optimum. So it means basically that we can change that by the amount that is indicated by the corresponding reduced cost component. But now the reduced cost depends obviously also on the basic variable cost components. And if a basic variable incurs a change, then for this new reduced cost, we have to employ matrix algebra there, because the basic variables part in the cost comes at the transformation that you take by multiplying with B inverse and N, because that's the part here that comes from CB transpose B inverse N is like, it's the net effect, the indirect effect of the non-basic variable to the basic variable. But it goes both ways. If you change the basic variables, then this is how it incurs a cost on a change in the reduced cost, which are basically the marginal costs of increasing those that are now 0. And if one of them becomes, if this means that one of them becomes non-zero, here's the algebra for solving that. And we just look at these corresponding ratios. And if the ratios are such that it may incur a negative change in somewhere, a positive change in others, and if it incurs a positive change, I mean opposite, the same, sorry, not negative, positive, meaning the same sign effect. So a positive cause is positive, or a positive cause is negative change. These are linear, so they're always in either the same direction or the opposite direction, depending on the sign. And we just pick two. We have to look at two different components: the ones that incur negative cause, negative change, and the ones that incur positive change, meaning the opposite direction and similar direction. And we just look at this net change, corresponding net change there. And as long as the change in the basic cost is between these two variables, that doesn't then flip any of the reduced cost into negative, then the change in the cost doesn't incur any change in the solution of the problem. And here's an example with two variables. It's got 4 variables in example 3.12, and here was the optimum, and here's the algebra is being carried out here. So as long as the change is smaller than 3/2, so we're good. The net change doesn't change the optimum. All right, I'm going to skip the interior point methods here. You can look at them if you want to. The interior point methods are based on this idea that instead of finding with direct linear algebra, instead of finding a feasible point by direct linear algebra, instead we travel kind of inside a region, and in this case, we can think of the dual. We are traveling inside the dual, adding a slack variable and looking at this, what we call complementary slackness before. You don't have to learn it, but you can look at how it plays in here. So we're kind of, the dual, the primal with the equality constraints is a little bit tricky to visualize, because then, you know, kind of work, you're kind of moving on the edges of a polygon in a higher dimension because it's equality. But if you're thinking of the dual, and with its smaller than or equal to constraints and free variables, then basically you are inside a polygon at all times inside the dual. And maximizing the dual, you know, you travel inside and the slack variable S in that at the lower end of the page is kind of the slackness. You can use the complementary slackness theorem there, so that as S variable there, once it hits 0 for a certain variable, then that certain constraint, sorry, once it hits 0 for a certain constraint, then that constraint has hit its limit. So you're at the edge of that polygon in some direction. And this interior point methods work by using the fact that there is that inside this dual you can then find the optimal, you know, starting from inside the region and trying to travel towards the it's still going to be some corner of that polygon that is the optimum, but you're traveling from inside, because in the simplex algorithm you're kind of traveling along the edges, or actually the corners. I mean, each of the basic solution is a corner point of the polygon in higher dimensions. And not going to go into detail how this is done. So there's this is the so-called primal dual interior point method. I'm not going to go there, but it uses quite heavy algebra, as you can see. We're not going to be doing this, but Karmarkar's algorithm, for instance, is a polynomial time algorithm. There's an interior point method there. It's not explained here, Karmarkar's original algorithm, but the primal dual algorithm is related to that. Not going to go in detail. It's not worth using too much time on here, because we want really from this, and why I want to wrap up this this linear programming theme quite quickly, is that linear programming problems, we solve them usually using software, obviously, you know, software we're going to be using otherwise as well. But why I want it to be here is that very often the case is such that the linear problem is the go-to problem. And if you take it to other directions here, there are algorithms that map into the successive iterations of linear problems where you add constraints or change the constraints. That's one way of looking at it. Then there's one direction in which optimization theory goes when you're dealing with discrete optimization, and integer optimization is the so-called integer programming problem, where you have a linear problem, the LP problem, but with integers. It's a whole different ball game, but obviously there also you need to solve a relaxed problem and then add some constraints into it to eventually find an integer solution. Branch and cut, branch and bound being the foremost algorithms they're using. Branch and cut is more efficient, yes, but a bit trickier to implement. Also the so-called mixed integer problems, where you have integer variables mixed with continuous variables. Like, for instance, your resource problem, maybe you need n, you need a integral number of certain objects. For instance, you need an integral number of let's say cars to transport what is basically a continuous variable, let's say some, the trucks. You need an integer number of trucks, and you're transporting a certain number of tons of concrete, let's say, and that concrete can be thought of as a continuous variable. You can take any kilogram number of it, and then the number of trucks is an integer problem, and so forth. So the mixed integer problems are usually, they're very, very common in industry. Sadly, we don't have too much time to enough time to talk about them here. I would much rather we had another course or two courses instead of one. So we'd have continuous optimization methods, which is this course, and then discrete optimization methods, which would consist of things like the mixed integer problem, programming problem. All right. Okay. So I know there's a lot of things to take in here. I think from this today's thing is what you should take in is the duality, how you find the dual of a problem and how you can use that to analyze whether the original problem is bounded. And you know, if the original problem is infeasible, then obviously the dual is also unbounded. That can be proven as well. That is really the takeaway from this. And what I want you to take away also is the idea that you can analyze a problem's parameters and their effect on marginal effect on the solution. And then, you know, if you are modeled a real life problem using it doesn't have to be related to just linear programming, but here was linear programming. The idea or the concept of analyzing the parameters of the problem, that come external parameters, and how the solution will change when and if, you know, whether it will change or what are the conditions under which the solution will be different. So that's actually, optimization is used in decision making quite a lot. In decision making, you know, you optimize something and you decide to go with the solution that is optimal. But that's just one part of it. The other part is understanding the problem that you just formulated and understanding that what if the world changes? You don't know the parameters, all the parameters, you know, 100%, you know, then analysis such as the one that we carried out today needs to be done. So I wanted to use this opportunity to just bring you and make you aware of this need. You know, we have to move forward here, but this is a good place to tune your mind into this need that may happen. The parameters may change, and you need to be aware that it's not just one-off. You optimize the problem and you're done. You have to be prepared for the situation where the situation changes enough that you have to do it again. And knowing beforehand how much change can you have before you need to do it again is a very important thing to consider when you're using it in real life. All right. There are a lot of problems here, and some of them are weekly exercises, not all of them. So it is actually something that you might want to revise and review more, you know, more in depth than we do at the exercises. The things that we ask at the exercises are the ones that I assume you will learn, but this can bring you into deeper understanding if this is something that you need or something that you wish to learn about. And in your modeling exercise, you can make use of this more in-depth material that is here if you so choose. I'm going to stop the recording now, and next week we will be talking about unconstrained optimization.